So let's start. Today I will discuss two important, or rather one problem which have two parts. This is actually from electric field. Actually problems on the basis of electric field. The problem is written on the board. Just see. Show that a normal component of electrostatic field has a discontinuity from one side of charge conducting surface to another, given by E2 minus E1 dot n is equal to sigma by epsilon naught, where n is unit vector normal to the surface and sigma is the surface charge density at the point. Hence show that just outside the conductor electric field is sigma by epsilon naught n. N is a normal, outward normal. And the second part is tangential component of the has a discontinuity. Component is discontinuous. Show that the tangential component is discontinuous from one side of the surface of charge conductor to other side. That means the problem is for a normal component it has a discontinuity, but for tangential component tangential component is discontinuous. Tangential component is not discontinuous. Tangential component is continuous. It's wrong. Sorry. Normal component is discontinuous and tangential component is continuous. This is the two part. The first part, which I have to prove, is that a normal component from one side of the conducting surface to another part of the conducting surface are not equal. Say one side normal component electric field is E2 dot n and another side electric field is E1, but the normal component of that two side of the conducting surface are not equal, and the difference is means that discontinuity. Continuous means normal component are equal. Discontinuous means normal component are not equal. So normal component difference is sigma by epsilon. This the first part. From that part we have to prove just outside the conductor electric field is sigma by epsilon naught n hat. And the second part we have to prove the tangential component is continuous from one side of the surface of charge conductor to other side. Okay, so let's start. Before we are going to do solve the problem, just try to understand to main concept of the vector. Okay, suppose this is a surface, okay, and this is a vector. Okay, one thing. Suppose A is IAX plus JY plus KZ. Suppose vector A is equal to IAX plus JY plus KZ. If I do a dot product A with I hat, we get what? AX, because I dot I only exists and I dot J, I dot K is equal to 0. So A dot I is equal to AX. That means when we do a dot product with a unit vector, we get the component of the vector along that unit vector. Just try to understand. If I do a dot product with J hat, we have only AY, because I dot J 0, I dot K 0, only J dot J exists. So what we get? We get we are actually we developed a concept here. The concept is that when you do a dot product of a vector with a unit vector, the result is the component of the vector along that unit vector. That means if I perform a dot I, then you get the component of a along I means x. If I perform a dot j, then we get the component of a along y means along y axis means a y. Similarly, say this is an electric field. This is our normal unit vector, and this direction we have another vector. This is called okay. This is our E vector, and n is normal direction of the surface. N is normal direction of the surface, and L is tangential direction of the surface. So if you perform E dot n, then the result would be normal component. If we perform E dot n, the result is equal to the normal component of E. And if we perform E dot L, then we get tangential component. Okay, na? Just like this, we perform a dot product with a unit vector, then we get the component of the vector along that dot product. Now n is the normal direction, so if we perform a dot product E with n hat, we get a normal component of E, and L is the tangential unit vector, tangential to the surface. That means L to be aligned to the surface. So E dot L gives us the tangential component of E. So these are the two basic things which we have to understand before solving our today's problem. Okay, I think you all understand. Now come to the point. So this is a charged surface. This side electric field is say E2, and this side electric field is E1. And we know E2 is equal to E1 is equal to sigma by 2 epsilon. We know. This side is a normal component, normal direction is this side normal direction is minus. Okay. In this side, in the region 2, say this is region 1, this is charged surface AB, which this side is charged, and sigma is the surface charge density. Then this side electric field is E2, this side electric field magnitude is E1, and E2, E1 from our earlier discussion, the result is sigma by 2 epsilon naught on both sides. Now normal direction is N in this side, and this side is, we can say this is N1 and this is N2, and we know N1 along this side, N2 along this side, so N1 is equal to minus N2. For this reason, we consider this is N and this is minus N hat. This is normal direction is N, normal to the surface is N, and along this side, normal to the surface is minus N hat. This is N hat, this is minus N hat. This normal direction is N hat, this normal direction is minus N hat. Since direction are opposite. But along the same line, along the same line. So, normal component of E2 vector. So, E2 vector normal component E2. Okay. So, what is E2? Then E2 is sigma by 2 epsilon naught N hat. Why E2 is that? Because we know for a conducting surface, electric field is always normal to the surface. So at this point, electric field is normal to the surface and n hat is a normal. So E2 is around n. And E1, similarly E1, at this point, electric field is E1 just perpendicular to the surface, and n hat minus n hat is the perpendicular. Electric field E1 is perpendicular to the surface and minus n hat is perpendicular. So E1 is equal to nothing but minus sigma by 2 epsilon naught n hat. This is simple. So E2 is sigma by 2 epsilon naught magnitude, and this is unit vector. This gives us a total vector. So E2 vector is equal to sigma by 2 epsilon naught, and n hat is the unit vector. And E1 is same sigma by 2 epsilon naught, but this is out of this direction, so minus n hat. Then E2 minus E1, so E2 minus E1 is nothing but sigma by 2 epsilon naught n hat minus E1, so again minus, so sigma by 2 epsilon naught n hat. So E2 minus E1, so this E1 is this, so minus 1 is this, so E2 minus E1 means this is E2 and this is for minus E1, and adding this 2. Or this is sigma by epsilon naught n hat. This is E2 minus E1, difference of electric field vector from this side and this side. Difference of electric field or the vector between this side and this side. What is the normal component? So E2 minus E1 dot n. What is the normal component? E2 minus E1 dot n. And E2 minus E1 dot n. This is our normal component. And this becomes sigma by epsilon naught. Already this is n hat. Now dot n hat. N hat is 1. So this is sigma by epsilon naught. So we see the result. Our result is proved that normal component of the difference is equal to sigma by epsilon naught. That means normal component of the difference is not equal. They have a difference. If this is equal to 0, then you can say normal component of the electric field is continuous. But since their difference dot n, this becomes a normal component, and this have the value sigma by epsilon naught, we can say normal component of the electric field has a discontinuity. So this is E2 dot n. This is the normal component of the electric field in this side, minus this is E1 dot n, means normal component of the electric field in this side. So there's a difference sigma by epsilon naught. This is normal component electric field in this side, this is normal component electric field in this side, and the difference of the normal component is sigma by epsilon naught. So there is a difference. This is our required problem, that normal component of the electric field is discontinuous from one side of the charge region to the other side, and discontinuity by sigma by epsilon naught. Okay, actually we have to prove this, only this much, sigma by epsilon naught, Now from this result we can prove, if this is our conducting surface, this is a conductor, from sheet to conductor, then electric field here U1 is equal to 0. Then what is the putting in this value, putting in this value. This is to this, putting in this equation u1 is equal to 0. Why? Because inside the conductor u1 is equal to 0. Since u1 is equal to 0, that's why u1 vector is equal to 0. So e2 vector is equal to sigma by epsilon naught n. What is E2? E2 is the electric field just outside the conductor. So from this result, you can easily prove if the conducting surface just outside the electric field, just outside the surface, electric field is equal to sigma by epsilon naught. E2 vector is equal to sigma by epsilon naught n hat. Or rather, from E2 we can say this is E is equal to sigma by epsilon naught n hat, and which is normal to the surface at that point. This is our first part of the question. Now the second part is that we have to prove that tangential component of the electric field just from one side to other side of the of any charge surface, means charge sheet, is continuous. This is our second part. In the first part, we have proved that normal component is discontinuous. Therefore, E2 minus E1 dot A is sigma by epsilon naught. That means there is a discontinuity. But for the case of tangential component, the tangential component, if we go from one side to other side of the conducting if we go from one side to other side of the charge surface, the tangential component remain continuous. So let's say this is our charge surface. So this is charge surface and positively charged. This region say 2, this region say 1. We consider a loop, say A, B, C, D. This is our A to B unit vector along A to B, and this is our unit vector along C to D. This is our unit vector along A to B, this is our unit vector along C to D. This side electric field is E2, this side electric field is E1. It may be in any direction, maybe in this direction or this direction, okay? So this side we consider only magnitude E2, this is E1. Now, taking line integration of the electric field in the closed path, this is called A, B, C, D path. dA, again come to A. So we are going to calculate the closed line integration of the electric field in this loop A, B, C, D, A. This line integration, closed line integration have four parts. One is integration E, one is integration E, one is E1, this is E1 in this side, this is E2. Then we consider this is L2 and this is L1, okay? So E2, this is two side, this is one side, so in this direction, this is L2 unit vector along A to B, and this is L1 unit vector along C to D. L2 is from A to B, L1 is from C to D. And also, we can easily understand that L2 is equal to minus L1. L2 is equal to minus L1 unit vector. L2 unit vector is equal to minus L1 unit vector. Now we are going to calculate this closed line integration of the electric field in the loop A, B, C, D, A. This closed line integration have four parts. One is E2 dot L to AB, A to B. One is this side electric field is E2, so E2 dot, this is unit vector L2 for the path A to B, plus second is from B to C, E dot DL. Third, again E1. Now this side electric field is E1 dot, from C to D, this is L1 unit vector, length CD, and fourth part is D to A, E dot DL. This four part gives us the total line integration around the closed path. Okay. First, A to B electric field is E2. So line integration means we have to go from A to B. So A to B is direction is L2. So L2 hat, length is AB. So L2 hat AB. Now from B to C, we don't know how this electric field. So we consider for B to C E dot DL. Now again for C to D, this is E1 dot. This side is electric field E1, so E1 vector dot. We have to go from C to D. So along the path C to D, unit vector is L1 hat into path length CD. This gives us the total CD vector plus integration D to A E dot DL. Now if we consider the loop in such a way that BC length and DL length are very small, that means BC and DL is nearly equal to 0. BC and DL is nearly equal to 0, and from this understanding we can easily cancel these two down. This is for BC and this is for DA, and we have only this part, second side, and this part for the first side. So just written here E2 dot L1 C. Okay. Now since the electric field is a conservative field, so for a conservative field, the work done or the line integration of the field around a closed path must be equal to 0. This is our condition. And I think I have proved it. The work done around the closed path is equal to 0. This is a condition to be conservative of any field. Here the field is electric in nature, that's why it is called electric field. And we know, like gravitational field, electric field is also a conservative field. That's why, from the property of the conservative field, the line integration of the field around any closed path must be equal to 0. So E dot DL, the closed path ABCDA is equal to 0. That means this is equal to 0. That means this result E2 dot L2 AB plus U1. Sorry, this is U1. So U1 dot L1 CD, that must be equal to 0, since the electric field is conservative in nature. So E2 dot L to AB is equal to E1 minus dot L1 CD. Now since AB and CD are equal, because we consider this as a rectangular loop. Therefore, AB and CD are equal. So these two terms cancel. So only we have E2 dot L2 is equal to minus E1 dot L1. But minus L1 is L2, so you can write E2 dot L2 is equal to E1 dot L2. That means, what is E2 dot L2? E2 dot L2 means, if it is, say E2 in this direction, say electric field in this side is in this direction, then E2 dot L2 means component of E2 along this AB. E2 dot L2 means component of E2 along this AB. That is called tangential component. And what is E1 dot L2? Say E1 is E1 dot L2. So E1 dot L2, L2 is in this direction. So what is E1 dot L2? So E1 say in this direction. So in this direction is E1. Then this is L2. Then E1 dot L2. This is E1. This is L2. So E1 dot L2 means E1 dot L2 is nothing but component of E1 along this path. So this is again tangential component of E1. So E1 tangential component. That means tangential component of E2 and tangential component of E1 in both the sides becomes equal. That means tangential components are equal. Although in the earlier case we have proved that the normal components are not equal. They have a discontinuity, means the difference of the normal component is equal to sigma by epsilon naught if you go from one side to other side. But although here we prove that if you go from one side to other side, tangential components remain same. So this is our problem. It's a very interesting and very conceptual problem. Students from the CBSE board try to understand. Okay, and if you have any queries, if you have any queries, then this is my number. This is my number 94342333811. This is my number. You can ask me any question on the topic. Now actually I am teaching over the total electrostatics. So if you have any queries on electrostatics from any chapter, if from capacitor or from electric field or potential or Coulomb's law or Gauss's law, you can easily call me. I will try to explain or I will try to resolve your problems. Okay? Till then, bye. Try to watch and try to understand.